Hi friends, welcome back to another video in which we will solve a particular problem, a relatively difficult problem from the book Strength of Materials written by Timoshenko and Gere. So here, in this case, we use a lever to tighten a shaft, to tighten a circular shaft as shown in the figure. So the shaft has a diameter D. We are using a lever and key mechanism. So key is the small rectangular piece which will be used to transmit torque from the lever to the shaft. So it is this small, this looks like this is a rectangular piece. So the first half of it will be in the lever as shown here. Let's say this first half portion will be in the lever and the second half portion will be in the shaft. That helps to transfer the torque from the lever to the shaft. The dimensions, this length is C and the cross section is square, so it is of uniform dimension. B in this side and it is B this side. Now the question is, once we apply a load P as shown in this particular figure at a distance of capital L from the center of the shaft, what will be the average shear stress developed in the key? So let's go ahead and solve it. Putting things into perspective, let's list down all the things what I have discussed just a moment ago. So I've listed out all of them here one by one. We are using a circular shaft. We are using a square key that fits into the slots in the shaft and the lever. Then shaft has a diameter little d and key has cross sections B by B cross B, a square cross section, and it is of length C. Similar to any other problem, the first step is to bring in assumptions. The skill of an engineer lies in how effectively he brings in the assumptions to the particular problem he is solving. So the few assumptions that we are taking into account for this particular problem is that disregard the effects of friction and assume a uniform distribution between lever and key. Uniform distribution in the sense uniform force distribution between the lever and key. So the very first step in solving this particular problem will be to draw the free body diagram of a very prominent component, which is the lever. So this is the lever which we were talking about. So here I have shown the free body diagram of the lever. There are two forces acting on it. One is the end force, which is acting at a distance capital L from the O point or the center point of the flange. Then due to the we are neglecting friction, so apologies that I use the word friction. So here there will be net reaction force acting on the lever because at this portion there is half portion of the key into the lever, so that half portion is B by 2. So at that region there will be a net force which will be Rk. Now how we will find what is the value of Rk? So Rk is a constant that we have introduced. It is not given in the problem. So can we express that in terms of the non-parameters? So here it is done. How it is done? Invoking equilibrium equations we can achieve that. So since this whole lever is in equilibrium, it is not accelerating, it is not moving. So if you sum up the moments about the point little o, as I marked here, which is the center point of the shaft, then I should get 0. So I did that. I took the moment about point O. So I took the counterclockwise moments as positive. So P into L, that end force will cause a counterclockwise moment. That's why here I have shown P into capital L. Then the reaction force from the key, it will cause a clockwise moment. It is acting at a distance d by 2 plus b by 4. Why b by 4? Because if this is that little portion of the key, I told you, let me draw it much neatly. You're just taking the moment about the point O. So this particular force Rk is acting at a distance of d by 2 plus b by 4. Why b by 4? Because this is how things are happening near the key. So only this half of the key is in touch with the lever. So only the contact pressure acting along that particular region will alone cause a force on the lever. The other portion is touching the shaft, so it will cause a force on the shaft. So it will be acting at a distance b by 4 from here. So that's why d by 2 will take you here, then extra b by 4 will take you here. So d by 2 will take you here, and then b by 4 will take you exactly at the point of application of the force. I have drawn it more elaborately in another figure where I have shown like this. So this is the front view of the key. Here what I have shown is a much elaborated and isometric view of the key. Apologies for my poor drawing. So as I was explaining you earlier, this portion of the key is in contact with the lever, while this portion is in contact with the shaft. Since we are looking at the free body diagram of the lever, an equal and opposite force will be acting on the key as well. So that force will be distributed like this, uniformly around on this particular half. Now there will be a resultant force due to this pressure distribution, which will be acting at a distance b by 4 from this particular end, because this is acting throughout b by 2. When you take the resultant, it will be at the middle, that is b by 4 from this end b by 4. Then that force will be trying to shear off this particular key, and the resisting area will be, think for a moment and come with an answer. So the resisting area will be this b. So if I draw that cross section along, it will look something like this. Then this dimension is c. I'm just isolating that particular cross section and drawing here. So my shearing area will be b times c. So now in order to calculate the shear stress, I know what is the force. It is the Rk reaction force from the key, and area is b into c. Now plugging in the expression what we obtained for Rk, we obtained a formula for Rk after equating the moment about the point O to 0. So Rk we found out to be 4pl divided by 2d plus b. Now let's take this equation. So that will be 4pl into 2d plus b into bc. So this is the average shear stress acting at that particular region. Just to verify whether units are right, yes, my units are right, because when you get an expression, just make sure whether units make sense. Yes, my units make sense, because P is in Newton, L is in meters, and 2d plus b, that bracketed term together will be in meters, and then we have a meter square. So together it will give me the units of Newton per meter square. That makes sense, because shear stress should have the dimensions of Newton per meter square. So this is the answer. Thanks for watching.